I'm Alex Bloom.
I'm Robert Knudsen.
And we are on the Trident cement plant and barrel moving project. Just a bit of a background for our project. We are working with our sponsor, that is Trident cement plant. They're located on Three Forks, Montana, right next to the Missouri River, and they have a nearby rock quarry. They use that quarry to crush limestone rock in large 10-foot diameter steel ball mills, and they crush this limestone down into a powder form. The way they crush it down is with golf ball sized steel balls, and these steel balls need to be replaced in the big drums probably about 4 to 5 times a year. This is where our project comes in. The way they transport these balls is with standard oil barrels, and they need a special apparatus in order to transport these heavy barrels, because the barrels weigh somewhere between 2,500 and 3,000 pounds of total weight. They want a mechanism that will have a much stronger clamping force, and the handle won't break as much. And they would also like this apparatus to be electrically powered. We want to have this thing rated for 3,000 pounds of total weight. The barrel weight varies depending on the full weight of the barrel, whether it's half full, quarter full, 3/4 full, etc. We want to make a safe-to-use design that's structurally sound and will last a long time. We are working with a $5,000 budget.
So, in analysis, we had to make some assumptions. The material we used for all of our steel members is AISI 1020 cold-rolled steel. We also assumed that the barrel was a standard size and uniform diameter, and that it was also strong enough to hold the components inside of it, like the bottom of the barrel did not break out when we were lifting up the barrel. Also, this barrel is used approximately 3 or 4 times a month for 5 years. So now we'll go into discussing how I analyzed all the different design criteria. Our shafts are analyzed using distortion energy theory. The bearings are analyzed using the catalog load rating. Chains are sized in accordance with the AISI recommendations. Motor transmission evaluated based on torque requirements. Sprocket sized in accordance with RPM requirements, and the frame has been evaluated using the SolidWorks or finite element analysis. The bearings we decided to use for this project are called cylindrical tapered roller bearings. We use these because they have a high axial rating. That means they're going to be able to handle a lot of force, like a weight force from the barrel. They also have a large radial rating, which means they can handle a lot of force in the radial direction, such as when the barrel goes around a corner. You need to be able to handle those loads. Well, the barrel itself requires over 10,000 foot-pounds of torque in order to fully rotate a half-full barrel, which is what we called the worst-case scenario. The best motor that we could find on the internet had 100 Newton meters of torque, and that's the output at the transmission. Sprockets sized in accordance with our final RPM required. The output of the transmission is 15 RPM, and we have to reduce that to about 1.5 RPM. So we're using a 2-stage gear reduction. The gear reduction in the first stage is 3.5 to 1, and the gear reduction in the second stage is 3 to 1, and that gives us our required final output RPM.
When we were considering our frame, we wanted to make sure that it was going to hold up to the forces and loads that it would be undergoing. We also concluded the shafts will break somewhere in the neighborhood of 85,000 cycles, but that's going to be quite a long time before they'll need to be replaced. So as far as timeline goes for our project, we're just now finishing up the design phase, and as far as the next 4 months, we will be ordering the parts here shortly, and we should expect to get them by the new semester and begin our machining and assembly. We'll have our product readiness review sometime in the first few months. We will also get some lab training for the Montana State Machine Shop, and we should be ready to roll from there. Towards the end of March, we should be working towards testing the actual prototype. We should have all the frame and everything designed up, or not designed, but completely assembled and welded, and then we'll start running some tests on it and see how it performs. And then we hope to have a working prototype delivered by the end of April, start of May, just as the semester is getting wrapped up. We will be working closely with our sponsor just to make sure all our specifications are met.